Let's talk about linear programming. Linear programming is used to find the maximum or minimum value of a problem that involves some constraints. For instance, companies might use linear programming to figure out the maximum profit they could get from products they are producing. And it was originally invented in World War II, or discovered in World War II, I should say, to figure out how much they could put on some of the airplanes that were headed over to the war front. They needed to carry as much as possible, use the amount of fuel that was needed, but have enough fuel to get there, that kind of thing. So after World War II, companies adopted linear programming to figure out their maximum because, of course, that's what they're interested in to make the mighty dollar. But let's just look at this little example I have sketched right here. Once you set up a problem with linear programming, you have a system of inequalities. And in your system of inequalities, you will have them form a feasible region. So after you graph them, there's going to be a region where all your shading comes together. So I haven't drawn all the shading here. I only drew the part where it had in common, and that is called your feasible region. Feasible means that it makes sense. So this is all the solutions that would even make any sense with our problem, but we're more interested usually as a company to figure out the maximum profit, like I was saying, and an energy company might want to figure out the minimum energy requirements. So maximums and minimums are our focus for linear programming. So you graph all of your lines, you figure out the vertices, and usually you're going to plug those back into what we call an objective function to figure out the max or the min, and we're going to look at an example in just a second. So the definition of constraints would be something like restrictions on the solution set. So graphically, they are our boundary lines. These are where if we go outside of these lines, then our answer would not even make sense with the problem. So those solutions are just not necessary. So we have constraints. And then the feasible region is just the area where your graph comes together with the shading. So let's write down the steps. For linear programming, you first need to define your variables. You need to write a system of inequalities that makes sense with your problem. You need to graph the system of inequalities and identify that feasible region, that place that makes sense on your graph with your problem, which is I put all shading overlaps, just as a note. Number 4 would be to find the coordinates of your vertices. And number 5 is to substitute the coordinates into the objective function to find your maximum or your minimum, depending on what they're asking you about. So let's look at an example. Let's say we're just given this really simple, straightforward example. Given the vertices of a feasible region are 4, 3, -2, -6, and -7, 2.5, we want to find the maximum and the minimum value of our objective function, f of x and y is equal to 5x plus y. So all we would do in this case is plug in the points they gave us to figure out what gives us a maximum and which one gives us a minimum. So I'm going to take 5x plus y, and I'm going to plug in my first point. So 4 was my x, 3 was my y. So I'm going to say 5 times 4 plus y, which was 3, would give me 20 plus 3, which is 23. Then I'm going to plug in the second point they gave me. So 5 times -2 for x plus -6 for the y is going to be -10 plus -6, or -10 minus 6 is -16. And then we need to look at the third one. So I'm going to say 5 times -7 for x plus 2.5 for y would be -35 plus 2.5 is -32.5. So you simply look at that point and see which one is the maximum. So maximum looks like we've got 23. So that's our maximum. It's important in the context of a problem, like when they give you a story behind the problem, that you realize that that x, let me write it over here, 4 for your x and 3 for your y. So 4 tennis shoes and 3 sports jerseys, if we're talking about like Nike's trying to make a maximum profit, just for an example. You need to have an identity of like 4 is equal to the shoes, and 3 might be jerseys, and it changes depending on your problem. But that specific thing, 4 of that, 3 of that, gave me a maximum of 23. So they can ask you about any one of those three parts. It's important to keep that all in mind. The minimum value, you can see, is right here. And the same thing is true. So for our minimum, it came from an x value of -7 and a y value of 2.5. So keeping that in mind, they might ask you about just that 7. What did that 7 represent? Why did it give you the minimum value? What does that y represent? And you need to know it gave you the minimum value. Let's look at one more example. Here we're given a graph that we want to graph the following system of inequalities. Again, it's very straightforward. There's no story behind it. We're going to do that on the next video. Name the coordinates of the vertices of the feasible region and find the max and min values of the objective function. So this adds a little more than what we did on the last example. We need to graph it first and pick out our vertices. So I'm going to try to keep my color coding going on here. So the first one looks kind of like a red. Y is greater than or equal to 2. So you go to y equals 2, and if it's greater than or equal to, we need to make a solid line, and we need to shade up above that line. I'm going to tilt my board a little bit so it doesn't fall on me. On the second graph, we have actually two things going on here, so you need to separate them. X is greater than or equal to 1. So if you want to write that out separately, we need to graph that part of what this statement says. So if x is greater than or equal to 1, we draw a vertical line at x equals 1. Greater than or equal to would mean...
Staff members, if you missed my announcement from earlier this morning, if you have not cleared
We're going to pause for that announcement.
Mailbox, please do so at this time. If you have not cleared all items from your mailbox, please do so at this time. Thank you.
My mailbox is clear, so we can keep talking. So the second half of this statement is x is less than or equal to 5. So let's go to 5. 1, 2, 3, 4, 5. Draw a vertical line at x equals 5. We want to shade where x is less than or equal to 5. So I'm just going to switch colors a little bit to make sure I keep track of where all of this shading comes together in a minute, because it gets kind of crowded sometimes. And our last graph is y is less than or equal to x plus 3. So we have a y-intercept at 3. We have a slope of 1, so I'm going to go from 3 up 1 over 1 to get this graph on my graph. And it's still solid because it's less than or equal to my line. And it's less than or equal to, so we shade in here. So here's where your final shading comes together, and you can see that this quadrilateral right here forms my feasible region, we're calling it. That's the proper terminology. And we want to pick out the vertices of our feasible region. Oops, I put that one a little bit too high. Looks like it should go right there. So it's good to be neat. Even if you're not normally neat, you want to try to be as neat as possible, since clearly there's a lot going on right here.
For the teacher that is in 2634, please go to room 2634 with your key. The teacher that is in room 2634, please go to the room at this time with your key.
So that point looks like it is at 1, 4. This vertex is at 1, 2, 3, 4, 5, and then up 1, 2, 3, 4, 5, 6, 7, 8. So 5, 8 is another one. This one right here is over 1, up 2. So we have 1, 2. And this one is 1, 2, 3, 4, 5, up 2. So now that's the part that was not included in our first example. Now we're going to do what we did in the first example and plug those into our objective function. So we're going to plug them in here and see which one is our maximum and which one is our minimum. So let's just start with 1, 4. So 1 for my x, 4 for my y, and I'm going to figure that out. Some of you might want to go ahead and write this down and fill it all in and then do your calculations in just a minute, because it's another way to organize our information. So I'm going to put 5 and 8 right there. The same setup will be for the third one. Let's put 1 and 2. We'll see what that gives us. 5. I'm doing this last one right here. And 2. So we just need to simplify. 3 times 1 is 3, minus 2 times 4, which is 8. So 3 minus 8 would be negative 5. We'll just make it a little darker. 3 times 5 is 15, minus 2 times 8 is 16. So 15 minus 16 is negative 1. 3 times 1 is 3, minus 2 times 4 is 4. 3 minus 4 is negative 1. 3 times 5 is 15, minus 2 times 2 is 4, so 15 minus 4 gave me 11. So it's easy to see now exactly where my maximum is and where my minimum is. And that would be the answer to that question. There's no story here, so there's no way to interpret what these numbers stood for. But if there were a story right here, you could talk about how the 1 for x, whatever x represents, cupcakes, candy, who knows, and the 4, whatever that represented, because you're going to define your variables when you have a word problem, gave me a minimum value of negative 5. So maybe it was a minimum amount of energy is a good one. And 3 times 5, the 5 for the x value, the 2 for the y value, you can talk about what they represent and talk about how they give me a maximum of 11. Again, we're going to get to the word problems in my next video.